spatial analysis with R language. Professor Lahssini, the research focus is related to forest sciences, forest resources assessment, forest modeling, and sustainability. Also, decision support systems, climate change, and forest management. Professor Lahssini has tremendous publications on adapting innovative technologies and solutions, which includes cloud computing solution for monitoring arid rangeland dynamics, case of Moroccan highlands and southern acacia ecosystems. Machine learning and remote sensing in mapping and estimating rosemary cover biomass. Also, monitoring protected area, big data-based approach. And Sentinel-1 and Sentinel-2 data for citrus crop management support and water monitoring. It's a great honor to have you as our speaker in this webinar, sir. Kindly requesting you to take over the session to educate us by your speech. Over to you. Thank you.
Thank you very much, Professor. It's a great honor to be with you this afternoon to try to share with you some insights, but also to try to learn from students to get some insights from you. So I will try to talk about precision forestry, what is, and with the focus on use of geospatial data and machine learning approaches. So I will try to outline my presentation as follows. So I will introduce forest management and precision forestry. What's the meaning of that term? So after that, I will go throughout the first pillar of precision forestry, geospatial data. So I will try to talk about traditional acquisition methods for data in forestry. Then we will go to geospatial data. After that, we will talk about what is the main characteristics of geospatial data, and then the workflow for analyzing geospatial data, either satellite data or LiDAR data. Then after that, we will try to talk about some issue of statistical modeling and spatial learning. We will try to get global approach. Then we will try to talk about some modeling example. So if we will have times, we will try to talk about what is the meaning of forestry for point 0, and we will conclude our presentation. So when we talk about forestry, forests as natural capital provide ecosystem services that are important for human being. It's contribute to sustainable development goals. So mainly it's contribute to provide good health and well-being for population, to produce water of quality, to have affordable energy, and to contribute to global action toward climate, in addition to other benefits that we take from forests, such as some provision to conquer to zero hunger goal, to have decent work and economic growth, to sustain cities and communities, but also it contributes to other aspects, such as in our less developed country, to alleviate the poverty, to improve the quality of education, gender equality, and to reduce inequalities and life below water. There is a lot of benefit that forests produce. So what is the main challenge that are facing now forestry? And we can give a question about what will be forestry without forests. There is a lot of trends. There is a lot of land use change that is due to growth of population, to climate change, with impact on the forest area. There is a lot of research extraction from forests, that are far beyond carrying capacity of ecosystem. There is also with climate change, there is a lot of fires, but also there is a lot of forest surface reduction, but also there is other ecological concerns, for example, biodiversity, wildlife, that will reduce our ability to harvest forests and to reduce the exploitation of forest resources. So what as forests we can do? So we try to improve our perception, our way of doing sustainability. So we try to implement larger scale, either temporal, but also it's spatial. We try to improve our way of doing forest management, but also we try to introduce new regulatory measures. But also, for example, in some countries, they introduced what we talk about payments of environmental service. It is in somehow environmental advance that try to compensate other service provided by forests, but that are not easy to quantify and to have amount of money. But also there is a very room of progression to innovation inclusion, and mainly for what we call precision forestry. So when we talk about precision forestry, there is a rising question. What is the difference between precision forestry and forest management? What is the explanation for two things? So what is forest management? If we can try to explain it's the process of selecting optimal activity for scheduling activities that will include one or more treatment option for forest sands. When we talk about forest sands, it's homogeneous subunit of forests with regard to tree species, composition, and age. So what we will begin, it will begin from knowing the resource, assessing the resource on forests, assessing their dynamics, and then depending on the market, depending on the availability of resource, we will try to schedule each activity to do within the time. So now, when we talk about precision forestry is somehow it's integration between all activities. Definition that I found is try to place the right tree in the right place at the right time, but also to manage it carefully, to manage its growth, health, to meet key quality and objective, and then harvest that tree based on market demand and deliver it in the right form to the right customer while minimizing cost and maximizing the value. It's in somehow integration between from what we call from seed to final products while optimizing all the chain. So within that process of precision forestry, what thing could be done? It could be done it goes from data collected to knowledge made from that data or decision made for data. When we talk about collected data, the collected data are related to either biophysical factor, to forest operation, to wood processing, to markets. Such data will be collected within the tools, either geospatial tools, GPS, remote sensing, but also sensors that will give information about to other software or to other tools for modeling purpose, for describing purpose, to get information, and such information will be used to help decision maker to get knowledge and to produce decisions that will try to improve the future of forest research. So when we talk of precision forestry, what is the main challenge? What's the main change from our traditional way of doing things? There is 2 or 3 main axes. First one is data that we'll try to get. So from common ground-based survey, we will try to implement more geospatial data, but which we use now, but also we will try to go further for some kind of sensors or some kinds of IoT integration in order to get monitoring of real-time monitoring of forest resources. So such integration could be done either at plot level, but also including some engines, for example, harvesters, seeders. It's somehow integration toward digitalization of forestry 4.0. So, but also when there is a lot of data, we will move toward big data for analyzing such data. But also when we talk about data, there is a need to move that data to information and then to decision and to knowledge. That require the use of machine learning or some modeling stuff. So we will try to focus mainly on geospatial data, on data needs, but also on modeling framework that we can use to move from that data to information and to help decision maker. So the first that we will try to talk is about data needs. So what geospatial technologies could contribute to forest management. So let's try to get a bite of what we have what we was used to do before geospatial data. Forestry was based on ground, either having aerial photography, so to get maps of forest resources. Then we have to go to a field in order to get data of research, forest research. Such data is related to tree level, but also to plots. Within the plots, we get information about research, and we try to model such data to try to explain how is the amount of research available now, and how these research will evolve in time, will grow. So in order to make projection for future. So now there is a big advancement that geospatial technologies brought for us. So remote sensing, for example, brought satellite imagery. So instead of using aerial photography, now it is easier to get satellite images of region, but also we can get LiDAR, which is light detection and ranging, which could give 3D point cloud that will be very useful for forest management. So we can classify geospatial data based on level of acquisition. So ground based, for example, using some drones that will not fly over than 150, or either using terrestrial LiDAR or using some optical stuff, for example, using hemispherical photography, or using airborne acquired data, for example, using plane to get either optical photography, aerial photography, or using multispectral photography, or using synthetic aperture radar photography images, or getting LiDAR data. But we can go further to get satellite images, which are less expensive and with high cover. So when we talk about spatial products provided by geospatial data. We can, as forester, we have a field which rely on forest research prevailing on the field. We can get satellite image, which consists of information beam. So each information will try to give information about spectral reflectance of surface according to some wavelengths. But also we can go, from example, from LiDAR, what we call point cloud. It's I will try to explain that. But also we can get SAR imagery, which is synthetic aperture radar images. So what is the characteristic of that spatial data? So first of all, there is a lot of characteristics. We will try to focus on three. Temporal resolution. What is temporal resolution? It's the frequency of return of sensors on specific area. It could give us the ability to detect change on spaces. So for example, for monitoring land cover change, we need repetitive images on same place. So for example, when we talk about UAV, when we talk about drone, we can plan fly every time we need. For example, we take sentinel images, we can get each image for the same place each 5 days. When we talk about Landsat images, even every 16 days, and so on. The second thing is spatial resolution. What is the spatial resolution? It's the very smallest piece of information that is presented by images. So it will improve our ability to detect smaller objects on the image. For example, we have the two first images at the left present the same place with two resolution. The first one 30 meter by pixel, and second one 2.5 meter by pixel, and we say the objects are more clear than in the left image. So in the right there is some objects taken by three instruments having 60 centimeter by pixel, 15 centimeter by pixel, and 1.6 centimeter by pixel. So there is our ability to have different view of things are improved within higher resolution. So what is the meaning of resolution, and what will imply for us? For example, when we are focusing on more global scale, we will try to get a bigger view. So of course we will try to have a smaller coarse resolution compared to when we focus on a field, on a plot data, on trees. So there is a difference between things and what information could be used for that. For example, when we try to analyze forest research at state level, at country, we will try to get, for example, airplane data acquired by airplane. When we are talking about stand, we can use drones, but we are at plot level. We need more field information. For example, we can use terrestrial LiDAR, we can use other research. The third characteristic of geospatial data is instrument resolution. We can instrument resolution. It's the ability to get difference between objects. It's, for example, when we talk about when spectrum, when electromagnetic spectrum, it depends on wavelength used. So when it's narrower, it gives us the ability to get more information on that data. For example, when we are using optical image, we are trying to have in 3 bands, red, green, and blue. So when we could use multispectral sensor, it gives us the ability to use 2 to 15 channel that will be used. And where the channel are narrower, the precision will be higher. When we use hyperspectral sensor, we can have a lot of hundred of channel that will be provided. So what is the meaning of such channel and or band of information? For example, each object has may absorb or reflect in some wavelengths. For example, when we take vegetation, that will absorb a lot of red color, but also will reflect a lot of infrared. So using just this band of information will give us the ability to differentiate between vegetation from bar soils, for example. When we talk about instrument resolution, for example, when we take light detection and ranging, for example, it is the higher, for example, for the case of LiDAR, it's the higher density of points returned by the instrument. So when we talk about LiDAR, it's in somehow sensor who send laser pulses that is returned by objects, and depending on the location of sensor, its orientation, but also of the time of taken by laser pulse, we can get the position of each obstacle in the field. So we can give us, when it gives us the ability to have much denser one cloud, it will give us the possibility to get more details and more information. So what is the use of that kind of geospatial data? So we can be used, all that geospatial data can be used for mapping, mainly for mapping, for example, land use, land cover, for getting information about the biodiversity, about disturbance, and about soils, for example. But also when we talk about LiDAR, it gives us the ability to get information about height of trees. So it will give us information about vegetation structure, tree heights, biomass, but also we can use it to get information about other stand attributes such as volume, such as biomass, such as what we call basal area. So there is a lot of information that we can extract from such thing. So what is the workflow below using the geospatial data? So before analyzing geospatial data, it's somehow there is some question about the presence of the ground truth data, about what kind of problem that we have, providing data. What is the approach that will be focusing? Is it object-based approach or pixel-based approach? What is the difference? It will be interested on defining objects or getting information about each point on the space. If we have interested about one time or multiple situation, and also if we are interested about geospatial analysis workflow will follow the scheme there. So in all, most of the time we have in situ data. In situ data that is related to forest resources. In situ data is in some sampling on which we could have either forest cover, either forest biomass, but in the same plots, in the same sampling ground, we will have reflectance of geospatial data, reflectance, for example, or information related to cloud data, point cloud data. We try to get information to establish a model between what we have in the ground and what is and the reflectance in such kind of floods. And when the model is developed, we can use it and derive objects. So there is two kind of information. Before using such information, there is a need for preparing our data. And the main question that is posed, is it categorical classification, yes or no? So if we have categorical classification for one scene or also for single scene, we can try to use digital number, but also if in the opposite side, if we don't have one scene, but we have different location, different time period, there is a need for atmospheric and radiometric correction of such image that will be used for modeling purpose. As I told, in situ data and satellite reflectance that is used within modeling framework to get model. And when a model is checked for robustness, for quality, it is used to predict for the future. So there is a case for example, for LiDAR. What is LiDAR? As I told, scanner will send millions of laser pulses that are reflected from trees, from ground. Then knowing the location of scanner and its direction, the objects, so the localization of objects could be defined and determined. So when combined with field measurements and having a model, it will give us the ability to produce to extract some attributes of forest research. The same case could be used with what we call terrestrial LiDAR. So terrestrial LiDAR, it's some disposal that we can put on the plot. Within that plot, we can get what we call the point cloud. So we can use it for classification. Then we extract trees attributes. For the special case of drone images. So drone images, it's somehow a small picture that is taken by image. It could be optical, but could include other spectral bands. So such treatment of that kind of image will produce two kind of products. So the first one is what we call orthomosaic. What is orthomosaic? It's to get one image from all the image taken by the drone. But from the other side, there is an interesting way using photogrammetric method. We can extract photogrammetric point cloud. It's similar to that one produced by LiDAR. It's not as precise than that, but it's similar. That can be used also for modeling purposes and for extraction. So I will try to So after talking about data used, so data, as we talked before, there is two things of information. There is ground data, but also there is what we can extract from geospatial research of that location. And there is a need to modelize ground-based data depending on spectral information, depending on characteristic of cloud or cloud points on that location. So there is a need for that, because when we talk about forest research, there is a lot of spaces when it's difficult to get all the information, and having some kind of model will reduce our ability will improve our precision, but also reduce the effort, the field effort. But also it can be used for either spatial extensive work, but also for time repetitive task. It's try to answer our needs of describing resources. It will be used for developing model, but also for analyzing changes that will occur and predicting the future of things. So there is a lot of question on which spatial modeling could answer. For example, what is the impact of droughts on trees' mortality rate? What is the impact of disturbance on carbon cycle on forests? For example, can we predict also distribution of vegetation 100 years from now? What is the impact of climate change on forest research? Can we predict the current distribution of vegetation, biomass, or volume across the landscape, but using only limited observation, not a lot of data? So spatial modeling rely on three main phases. So first one is data collection, and we talk about data collection. There is the two things. First one, the on-field, the ground truth, the field extracted data, and second aspect is the spectral surrogate variable, or that we can, or other information that can we extract from remotely sensed data. So after getting data, the first thing to do is to extract the data of the location for each plot of each layer of information. For example, when we talk about optical images, we have three bands, red, green, and blue. So we can, to simplify, we can extract for the same location all information or spectral information of that information. Then when such information are extracted, we go towards modeling approach, like some tabular modeling approach. And we talk about modeling approach, there is all time one dependent variable. For example, when we try to modelize the biomass, which is Y, that will be tried to be modeled knowing the X's, knowing the predictors, the predictor which has the spectral information within the band. So there is two ways to establish such a relation, either using parametric model. For example, when we try to parametric model, it depends on, it have assumption about the distribution for data, and also of epsilon, use the errors of the model. For example, we can do maximum likelihood classification, discriminant analysis, general linear modeling, for example, linear regression, it will be used, or other non-parametric models such as machine learning or other models that could be used, general additive model, artificial neural network, deep learning, or other things that could be used. When our model is fitted to our data, so there is the third step is to evaluate our model, to validate it, to assess the overall accuracy, to get kappa value, to identify omission and commission error, and then to use, when the model is of good quality, to use that model to the predictor used, and then to get thematic maps, or also to get tabular information such as statistics that will be used. So let's try to share with you some modeling example that we try to do, just to be simple. For example, mapping forest stands. So before managing forest resource, we need to know resource available. So the first thing to get, so try to predict the distribution of vegetation throughout the landscape using some environmental variables such as geology, topography, climate, spectral information, but also other information gotten by remotely sensed imagery. Information on field are fitted, so statistical models are built by finding the relationship between vegetation data, between ground data, and available digital data that we predicted, such as spectral information on that site or other information, topography, climate, geology, in order to get a model of good quality. When the model is of the good quality, we use such model in order to predict on all the space to get information about forest stands. For example, there is an example on which we has used the same case. We mapped forest stands in Middle Atlas in Morocco. So we try to get distribution of species based on knowledge of fields. So on one hand, we get spectral information about sentinel images that has been corrected and atmospherically and geometrically corrected, clipped to study area, but also we derived a lot of spectral indices that will be used, and then we train the model, train the model to get the best prediction of forest stands. The same case, we use it for rosemary. Rosemary is a plant that prevail on arid lands on eastern part of Morocco. And we try to we need for management purposes, we need to know forest resource available to map that resource, but also know forest availability of resources. So we got almost 200 training sites that has been used to identify either the amount of rosemary, but also its cover on the field. Then a model has been built using a random forest classifier to get map, but also regressor to get biomass for the thing. Another modeling example is to predict climate change impact on species distribution. It's we use the DAS modeling framework for modeling the impact of climate change on 3 Moroccan species: cedar, Atlas cedar, Quercus subur, but also for Argania spinosa, which is a species of the southern part of Morocco. What we do, we try to get plots on which we identified if the species is present or absent, that it's ground data. On the other hand, we get information, other predictors. Such predictor were mainly bioclimatical predictor. We used 19 bioclimatical predictors, including temperature and precipitation, rainfall, in addition to other predictors such as elevation, slope aspects. We tried to model the probability of presence of species, knowing the other dependent variable, which are elevation, slope aspects, and other bioclimatic variable. When the model is fitted, it has been used to generate map of species occurrence actually now, and then this model have been used with projected climate, projected future with the climate future projection using the 4 RCP scenario in order to analyze the impact of climate change on species distribution. So there is some example that has been used either for oak, for carob tree, for Argania species. Also, there is another example for predicting susceptibility to goodies. So what is the goodies? Goodies are a form of soil erosion. So we try to get information about presence of goodies on one hand, on the other hand, as dependent variable. On the other hand, we get other predictor related to topography, elevation, slope, exposure, slope length, and other information related to soil occupation, soil cover. Such data were being divided into a data set, one for training and the other one for validation, 85% for training and 15% for validation, in order to assess, to fit a model. A random forest model have been used to assess the probability of having goodies within a field. Such kind of information of map could be used for decision-making purposes to act toward protection against that problem. Another modeling example is using LiDAR data for forest research assessments, and data has been used. So we used in that case we used mainly drone images from which we derived point cloud that has been used with field measurements in order to detect either trees, but also to establish relation between some forest attributes like as basal area or volume with the point cloud metrics such as mean of the plot, such as standard deviation of information, such as percentiles of height, but also of cover fraction, which we have. So what is I think there is a lot of information, a lot of perspective that has been brought by development of new geospatial technologies, but also new device for extracting information. We move toward from data to big data. We're used to use huge data, but we will move toward big data, which will imply a lot of change of our way of doing things, but also of our way of using of our habit. But also there is a lot of data access now. There is availability of remote sensing images. For example, 10 years earlier, we cannot handle having a lot of satellite imagery. Now we have access to such information. There is a lot of trends for spatial modeling and particularly for forest management, trends for getting more reliable, more reliable model with biological systems, but also there is a need to go beyond wood as main products to include other products to move toward multi-purpose forest management. There is global need, as we know, forests contribute to global action toward climate, and there is a need to assess carbon and biomass within forests, to assess dynamics of dead wood and other stand characteristics that are very difficult to get from, for example, a common satellite imagery use, to get more information about wood properties, to get more precision about resources available, but also to integrate different sources of information into forest inventory. For example, source from coarse information, which is used for national forest inventory, information that is more precise for forest management, but also other geospatial available data. But also there is a trend to get more integration toward the whole value chain. And we will, about integration, we will brought us to move forward toward forestry, digitalization of forestry, what we talk about toward forestry 4.0. So now, as we are in civil engineering institute, I think there is a lot of things to think on, mainly on the integration of devices to assess forest research, to get more integration between action done, and to move toward more improving information. So, in order to not be so long, I will try to conclude about question that we can do. What will be forestry without forest? What is the main challenges of that has been brought by precision forestry? Until now, we still face limited knowledge of forestry research. And I think all that availability of data will bring information and will bring issue to such problem. There is a lot of scales on forestry research, so we can think at plot level, but also we can think at watershed level, at national level, and there is the decision will differ depending on the scale of interest. But also we can take temporal scales. For example, when we talk about forests, when we plant forests now, we are sure as forester that the product will be maybe seen by future generation, and such temporal scale is very important to take into account. Also, there is a need to move toward multiple function of forest resource. In our context, for example, forests are in somehow social. There is a lot of people that are living from forest research, and there is a need to have a balance between all the function. And now we must use all the data to optimize the provided function. Also, there is deficient investment. There is not enough investment in forest research. So how precision forestry could contribute? For example, when we talk mainly about geospatial technologies, but also we can move forward to Internet of Things, to what we call Forestry 4.0 toward more integration, to go from seed, for example, to final products. I think there is a lot of perspective on which we can all together work together. So there is a perspective on which we have to move forward. For example, thinking about the integration of big data. Unfortunately, we did not talk a lot about machine learning, how data analytics could improve our way of doing things, how could bridge the gap between knowledge or availability of knowledge, but also research that are not very important. There is also need to improve our way of optimizing tasks, but also when we talk about forestry, we must not forget the social dimension. And we talk about social dimension, the question of if the information technologies could help as social platform to bring consensus about forest conservation. I think I try to respect the time. I would like to thank you very much for your listening, and I am, if there is some question.
Thank you for the wonderful presentation, sir. Here is the question from the student.
So in terms of precision forestry and forest management, the overall data acquisition system poses a difficult task as the monitoring of the features that change and evolve continuously. So how can we tackle this without conventional methods?
So, sorry, will you please repeat?
Sir, in terms of precision forestry and forest management, the overall data acquisition system poses a difficult task as a monitoring of the features that change and evolve continuously. So how can we tackle this without conventional methods? Should I type it? So I'll repeat once again. In terms of precision forestry and forest management, the overall data acquisition system poses a difficult task as the monitoring of the features that change and evolve continuously. So how can we tackle this problem without conventional methods?
I'm not so sure if I got very your question, but I will try. You told that how position system will improve our think in precision forestry and forest management.
Yes, sir. Data acquisition system. Data acquisition.
Okay. So when we are talking about, for example, forest sand, the precision is something that is important, but is different, for example, from a civil engineering perspective. I will talk about error, for example, for establishing forest cover maps. Now, for example, in Morocco, when we are talking about lands, it's almost 10 centimeter precision, but we are talking about forest map at national inventory. We could accept error that's not far beyond 50 meter, and the precision is something that is more important. So there is, for example, when we are working on forestry, there is data that is acquired by geospatial system, but also data that is field related on that is expected from field. And of course, there is there could be a gap between precision of two way of acquiring information. For example, when I talk about the modeling example of using drone-based cloud ponds for assessing forest resources. So we got that problem. We used GPS, traditional GPS. So instead of having information, we got some spatial errors that is related to the precision of data acquisition, which is GPS compared to information gotten by drone. So I hope that I give.
Yes, sir.
Thank you.
Good afternoon, sir. My question is for a country like India, which is having vegetation of more than 8 million kilometers square. That is some sort of vegetation. We have like 8 million kilometers square. So, the variety of the vegetation in India is also massive. So how can this model of precision forestry can be applied for this sort of vegetation, so to make it more sustainable and cost effective?
Thank you very much for your clear question. I think there is, we are facing a lot of challenge. So when we talk about our countries, so we talk about forestry on social context. There is a lot of people that are living from forest resources that depend for their incomes for forest resources. And such case, for example, we know forests are playing a major role for global preoccupation, for example, for carbon sequestration, but also for social people. So there is a need to sustain forest research. There is need to think about forest research not as something that we have, but something that belongs to our children, to our. So we have to pass in good ways this research to a future generation, and to do that there is a need of sustainably managed forest research. The thing is so difficult in case of having a wide range of vegetation, but having in account that there is not one way, but there is a multiple way on which precision forestry, on which use of tools are very important. Indeed, for example, managing forest resource, such a resource, there is need to assess that resource, to know what is as a resource. So such need could go from having map of that resources to having more quantitative information about the variety of vegetation that is that prevails. So on that way, either for having maps or either for having precision on resource available at that time, there is a need of tools. So tools could be geospatial data, but for example, within your institute, as we, for example, for developing future sensors, for developing other things that could be useful for future of our research. I think your the combination of efforts of forester, for engineer, for other informatician will be very helpful to protect natural forests as natural capital. Thank you very much.
Thank you, sir.
तो खाया मम्मू जो बच्चा खिलाए नहीं क्या मम्मा तुम्हें मम्मा
So as per India's time zone, I must be wishing you good afternoon, sir. So my question is, what are climate data and how do we actually assign numbers and values to them for analyzing and forecasting the optimal results in precision forestry?
Sorry, how climate data?
I'm repeating the question, sir.
Thank
What
you.
are climate data and how do we assign actual numbers and values to them for analyzing and forecasting the optimal results in precision forestry?
Thank you very much. As for example, when we talk about distribution of vegetation, there is ecological factors that determine the distribution of vegetation. So such factors include either climate data, but also it include other surrogate variables such as soil, such as topography, such as other things. So when we talk about distribution of vegetation, there is need of knowing climate data. There is two kinds of information. So when we talk about climate data, we think almost the time there is a kind of station on which such climate data is delivered. So there is on somehow punctual information about related data. For example, when we talk about temperature, now at here in Rabat, or for example at Bangalore or at Delhi, so there is information that is measured in that location. But knowing, for example, if there is a lot of station, we could do some kind of spatial interpolation of each factor to get map of, for example, rainfall, for temperature, etc., etc. We can do that, for example, using station, but also we can use some other derived from satellite images, as land surface temperature. We can get it from satellite images. So how to get map of factors. So for example, when we talk about climate data, for example, it's somehow chronological time series of information. For example, from 1st June to 31 December. So we need to get somehow how to aggregate some information. So that information, that 365-day information. So we use what we talk about. We use some aggregation. For example, with one aggregation that we use almost of us is using annual rainfall, the amount of rainfall used each year. But also, for example, in arid lands, we can speak about rainfall during the summer, rainfall during the winter, etc., etc. For example, for modeling purpose, we use 19 bioclimatic variable. So 19 bioclimatic variable include, for example, rainfall during summer, rainfall during winter, rainfall during the year. What we called also, there is also other bioclimatic variable. I can send you a list of bioclimatic variable that we could use. So that's variable, but that bioclimatic variable rely on some historical analysis to get, for example, to link between the presence of species now and the current climatic condition. When the model is assessed, for example, to forecast the future distribution of the species, what we do, we have the dependent, we have the model. When we have the model, we can use the forecasted climatic condition. And using forecasted climatic condition, we focus on using the projection made by l'IPCC, to, for example, for 2050 and 2070, to get to forecast, for example, the future of distribution of species. I hope that I clarified to you.
Yes, sir, it was really helpful. Thank you so much.
Sorry for my English. My English is not so good. I'm a French speaker. I do my best to try to explain to you. Thank you.
Asking all the questions. Now we have come to an end. I request Professor Nisar Ahmed sir to give a vote of thanks.
So good afternoon to all. So indeed, on behalf of entire RIT family, my colleagues, staff, students, I'm very much thankful to Professor Lahssini for accepting and delivering this wonderful lecture. In fact, the focus on precision forestry, data centric, the modeling example, then the forestry 4.0. In fact, so somehow our students are familiar with the construction 4.0, industrial IR 4.0. So now they have a fair idea about the industry 4.0. So your explanation, your presentation with the real-time modeling, so it has definitely it is benefited to our students community. So once again, on behalf of RIT, so thankful to you for your presentation, your time and services. So take care. Bye.
Thank you very much, Professor Nizar. Thank you very much for your listening. It was a great pleasure of being with you. Sorry for my English, but I will try to progress, and I hope that next time will be better than that. Thank you very much.
Good. So tomorrow, so tomorrow being the last session, last day, we have 3 sessions. The first session from Dr. Prashant Motwani, specifically on IoT and sensor. So he is delivering from Singapore. The second speaker, Dr. Krishna Reddy, he is a professor, University of Illinois, Chicago, from USA. And then the last speaker, Dr. Ramrao Madhuri. So he is, in fact, his main focus will be smart cities and master planning. So please join with us. It's very informative for tomorrow's 3 sessions. Thank you very much. Oh, if I say timings, tomorrow you won't come. Before your class will inform. But now it